Alright, welcome back. So, we were discussing formulation of DIC and we were going to derive the equations for an iterative scheme for determining the displacement fields and its gradients for a solid deformation. Before we start, just to make sure that we are all on the same page and we are up to speed, I will just backtrack a little bit and continue from where we left off. So, this is where we were. We had discussed this idea of undeformed configuration on the left and a deformed configuration on the right, and we said that the aim is to determine this mapping called, which we called chi, which takes the undeformed configuration to the deformed configuration. And we, to do this, we take a subset at a particular point in the undeformed configuration that is marked over here, and we search within a search window in the deformed configuration, and we try to find a good match. Again, I put this good match within quotes because if you recollect, we discussed that for fluids the only thing you need to match is a rigid translation for this subset, because points are all moving around. But in the case of solids, you have this additional problem that the section can be deformed, the subset can be deformed by itself, which means not only is the rigid body displacement important, which we have denoted by u and v, u being the horizontal displacement, v being the vertical, but also you have to worry about shape change. So, which means the gradients of ux, uy, vx, vy and rotations, right. So, this square can rotate by some arbitrary angle at each particular point. So, you need to now look at 6 parameters when making this search from the undeformed to the deformed configuration. Now, this makes the search a little bit more complicated because you have 6 variables, but additionally it also puts constraints on the image, right. So, you can't have any type of image in which you can get a successful search, and we discussed 2 of these problems. I had introduced this reference by Steyer, Otiu and Sutton, and I showed you a couple of problems, the correspondence problem and the aperture problem. We discussed that also in the last session, and just to make sure that our notation is clear, this is what we had used. So, f was our undeformed image, g is our deformed image, and we also realized that you have to use a speckle pattern in the image and then follow the speckle as it deforms. You can't have an infinite lattice because then that will lead to a correspondence problem. You can't have infinite lines because that will lead to an aperture problem. Now, to do this search, you start with a subset inside f, like I mentioned here, and you look for translation, deformation and rotation, okay, which means translations like we saw are u and v. Deformation, which is basically the strain, has 3 components in 2 dimensions. So, that is ux, vy, which are the tensile or the stretch or compression components, and uy plus vx, which is the shear. And there is also a rotation component. In 2D there is only one rotation component. So, you have 6 unknown variables u, v, ux, uy, vx, vy, and you have 6 physical operations that are potentially performed to a particular subset S. So, that is the u, v are the translations, ux, vy, uy plus vx are the shear plus stretching / compression, we generally call them deformations, and you have the rotation uy minus vx. So, 6 represented in terms of 6. Alright. So, the heart of this entire scheme of course is this guy called the correlation coefficient, which we have denoted by C, sometimes called CORR, so notation might vary, and it is defined as the following. So, you take the search region which is S, the subset which is S, and for every point location inside S you evaluate f at xy, that particular point, minus g of x tilde y tilde. Now, x tilde y tilde are deformed values of x y. So, you have, let us say, some value of p, p being again this, so this is your 6 dimensional. I am going to use a column vector notation for this just to be consistent. It does not matter, you can flip, transpose everything I am going to show and still be consistent if you wish. So, this is the 6 component vector p, and x tilde y tilde is obtained by adding p to x comma y. Okay, so, you have x comma y, you do Taylor series expansion, you will get x tilde y tilde, and the first 2 terms in the Taylor series expansion are the translation terms and the gradient terms. Okay. This we will work out the algebra today, but at least I am just giving you an idea before we start. Now the whole point is you do this, let us say for some arbitrary p, you could think of this being a 6 dimensional space for instance with axis u v, u x, u y, etc., and pick various values or 6 tuples for this vector p, add it to x comma y and get x tilde y tilde, and then find out this sum, this difference, and square it and divide by f. This is again just done for normalization, it does not really matter usually, and then you find a c. So for one particular value of p bar you get a c. You can do this for every single value of p bar, you can change u by a little bit, you can change v by a little bit, change ux by a little bit, blah blah blah, and get different values of p bar, different corresponding values of c. You collect this entire set of values of c and then you look for the smallest value of c or an extremum value of c, and at that value of c the corresponding p for which you get the smallest gives you the actual p. Okay, that is the idea. So the correlation is highest when you do this type of a thing. So we will continue from here. I will do the formal derivation a little bit to evaluate this iterative scheme that we mentioned, and we will see how you can do an implementation based on this iterative scheme. For determining the final p. So this is the actual p bar for a subset S. Now remember, this is a function of the subset. So for different parts of the image you can get different values of p, which means that you will naturally expect that if the deformation is non homogeneous, various values of displacements and its gradients at various locations, and this entire iterative scheme is for one particular location. So you typically will start with a grid and iterate, do the scheme at every single point on the grid using a window subset and a search window for every single point. Okay, I will show you an implementation again in the next session hopefully, but today we will set up some of the structure for getting there. Okay, now before we develop this iterative scheme, we will just recollect one small bit of information that I also introduced last week, which is the fact that f and g, as I will show you, are represented in the form of a bicubic form. Okay, they are interpolated. So we discussed this at length last time. Likewise for g, x tilde y tilde are coordinates in the deformed image, and this bicubic form allows us to take derivatives. So for example, if you remember in the original image you typically have x y as pixel locations, so they are all integers, and the intensity, if you have an 8 bit image, the intensity goes from 0 to 255, or 10 bit it goes from 0 to 1023 and so on. And so typically f is an integer valued function, g is also an integer valued function, as are x, y, x tilde and y tilde. Okay, these are also integer valued because pixel locations are integers. So by doing this bicubic interpolation, it allows us to take derivatives, second derivatives specifically, as we will see, and makes them also continuous. So second derivatives can be defined very easily, and you will not lose data as you go taking higher derivatives. Okay, just something to keep in mind. So all the gradient expressions that I will write down, they are all with the view that you have this bicubic interpolation underneath. Okay. So for instance, you can actually evaluate, if you want to evaluate dou c by dou pi, right, pi being one component of the vector p, you can easily do dou c by dou x by dou pi using the chain rule for instance, or dou c by dou x tilde by dou pi, you can do plus dou c plus dou y tilde by dou pi and so on. So you can do these types of chain rule applications without worrying too much about whether your image has enough resolution and so on if you have this bicubic interpolation. Anyway, we will see this as we go along. Okay. So, the long and short is the following. The idea that we are going to use, so the main idea is to expand C of p about some point p naught. Okay. It does not matter what point this is, just an arbitrary point, we will make some sense out of what point to use at the end, and we will do this expansion using Taylor series, simple Taylor series truncated at 2 terms. Okay. Now, remember p is a column vector as I mentioned before. So, please keep this notation in mind. So, it is a 6 by 1 matrix, 6 columns by 1 row. I am just using this notation so that we are consistent in all the expressions we write down. So, this is our p vector. The p is useful for writing x tilde in terms of x and y tilde in terms of y. So, for example, this is typically what x tilde will look like. Okay. So, if you think back again from our discussion about the difference with fluids, the first term here represents a translation. So, if you had a square, this is the center of the square and this square is in the undeformed image at the location x comma y. The first term alone, right, if you just keep the u and v terms, it means that this square is getting moved, translated, rigidly translated to a particular location x tilde equals x plus u, y tilde is equal to y plus v. Now, in addition to this, the second term has this delta x delta y that is dropped in. So, it is no longer just dependent on the center location, but it also depends on locations within the subset. Okay. So, if you have some point that is delta x comma delta y away from the center, that point will correspondingly move to another location here given by these terms. Okay. So, you have a stretch or you have a rotation, that is what this means, right. So, this Taylor series, this one is just giving you the stretch, this one is giving you one component of the shear plus the rotation, and this is analogous. Of course, you have higher order terms that will include second derivatives of the displacement and so on, and you will have more components to worry about, but we will just assume that since we have a 6 component vector p, we will assume that these are the only terms you have to worry about. Okay. All right. So, in order to determine this, I said we will expand C of p about p naught. So, the expansion goes something like this. The first term of course is C of p naught and the second term is this. So, this is the second term in the Taylor series. This is similar to if you had a function f of x and you are expanding about x equals x naught, you have the first term f of x naught and second term df by dx times x minus x naught, this is like that term. Okay. Now, notice that grad c rather p minus p naught is a 6 by 1 like we have here above. So, it is a column vector, this guy is a row vector. So, it basically has dou c by dou p1, p1 being u, dou c by dou p2 and so on. So, this is nothing but dou c by dou u, dou c by dou v and so on, dou c by dou vy. Okay, that is what this is. And then you have another term, we will keep 2 terms, you will see why. We will have another term which will be the second order term in the Taylor series, and that will look like this. And higher order terms, okay, which have larger additional derivatives on C. This is called the Hessian matrix. This is called the gradient matrix. Okay. And just this factor of 2 of course is the 2 factorial that you get in a Taylor series, typical Taylor series expansion. So, the next one will have a factor of 1 by 6 and so on, 3 factorial. Just to be sure, this being a 1 by 6, this being a 6 by 1 will give you a scalar. You have a row vector times a column vector here. Likewise, this being a 1 by 6, this will have to be a 6 by 6, this will be a 6 by 1, again you will get a 1 by 1 which is the scalar, right. So, you should have by 6, 6 by 6, 6 by 1 for this. Okay. So, notice there is a transpose here. So, this p bar minus p 0 bar transpose will be a transpose of this, the 6 by 1 will be 1 by 6, right, which means the Hessian is a 6 by 6 matrix and it is not very difficult to guess its form. It is basically this second derivative of C, right. So, this one will be dou square C by dou u dou v blah 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 and so on. So, these are all second derivative matrix. Okay. So, you have C of p this notice also this is evaluated at p equal to p naught. So, please remember that. And this is again I am just writing down what we had on the previous slide. This is again at p equal to p naught plus blah blah blah. Okay. Now, this gradient is gradient with respect to p, just like this second derivative with respect to p, right, it takes with respect to u and v and so on, right. So, this is with respect to p, this is also probably evident in the expression we wrote down for the grad p grad c sorry. So, the gradients again are evaluated at a particular point. So, they are constants. Okay. So, I will just take a gradient on both sides of this with respect to p and transpose the entire final result. Okay. If you do that, the first term will just be grad c of some arbitrary p transposed. The first term on the right hand side will be 0 because it is a constant, remember this is a constant evaluated at p equal to p naught. So, that will go away. If you do the same thing on the right hand side with the second term, this again a constant, it will come out and then this has only p bar minus p 0 bar, but since you are multiplying through a matrix and you are taking a transpose, gradient of that with respect to p will give you just identity, right. So, then you will just get this, which is again grad c at p 0 bar transpose, and if you continue this process to the second term, again you have a constant sitting in the middle and you have a term on the right hand side. So, I take a transpose of this entire thing, take a gradient like I said before, the gradient p of this term will give you identity again, gradient p of this term will give you another identity, you have a factor of 2. So, the two of them will add up to give you just one term. So, you will get p 0 bar minus p 0 bar. Okay. So, this is a if we go back you will see that we had defined gradient C transpose as a 1 by 6 matrix. So, this is 1 by 6, this is of course 1 by 6. P bar was a 6 by 1. So, you should have a transpose here. So, this will be a 1 by 6 and this will be a 6 by 6. So, the whole thing will give you 1 by 6. Okay. So, it is just bookkeeping, there is nothing deep or sophisticated about this, it just make sure that you have the same consistent notation throughout, there is nothing else to remember. Okay. So, if you do that, now we have this relationship, and if the at the actual value of P, remember we said that this gradient of C is 0 because C is an extremum. So, if we actually have the displacement slash shear slash stretch slash rotation of that particular subset, then the value on the left hand side should be 0, which means that this grade C on the right hand side should give you 0, okay, it should add up to 0. Now, you can shift the second term on the right hand side here and rewrite this expression as, and take a you can take a transpose again, and it does not matter on both sides. If you go back, I had a Hessian term on the right hand side. So, I will have an expression like this. With a negative sign. Okay. So, from here I can write down P bar is P 0 bar plus, sorry, rather minus grad C P 0 bar divided by, I am going to be a little bit loose with my notation, divided by the Hessian. You actually have to do an inverse because these are matrices. So, maybe we will write it out in the correct form. So, this will be okay. So, this is basically the only equation you will need for the iterative scheme. So, let us say you start with a value of P naught. This is your initial guess, so to speak, for the entire 6 component vector. You can just evaluate these guys because all of them are done at C. You can evaluate these guys and then get a slightly better value for P. Okay. It still will not give you the minimum because if you evaluate C of P after one iteration, typically you will not get the actual minimum. So, you will get another value which is slightly better than the first guess. So, then you take this and you iterate. So, this is so you start with P naught, let us call this equation 1, and then you calculate P 1 is equal to P 0 bar minus the Hessian at P naught inverse times the gradient at P naught, and you take this and you repeat it. So, you calculate P 2 is P 1 minus now grad C inverse at P 1, grad C at P 1 and so on. Okay. So, in general after the rth step you will have P r plus 1 is P r minus this Hessian evaluated at P r again multiplied by the gradient evaluated at P r. And notice also that this subscript I am using here is actually an iteration index. This is not an individual component, I am using a vector notation. So, this is not an individual component of P, it is the iteration index, and you do this as a purely matrix equation. So, you will have a column vector on the left and you have a column vector on the right, which is the sort of correction term after every iteration. Okay. And you continue this until you get some convergence, right, until you get until your additions become so small that the value by which p changes after the rth iteration becomes very negligible. So, at that point you can stop the iteration and the final value, this gives you the final value of p, and remember this is for the particular subset S, okay, where this is all performed. Now, this is a fairly simple scheme. So, typically what you will do is you start an image, you have a grid on an image. I will show you some of this implementation in the next session, and at each grid location you have a subset. You look at the deformed image in a search region, get this subset out and map it to various locations and various shapes and so on. That is essentially what you are doing by doing this iterative scheme, and depending on where it matches the best, where you get the lowest value of C of p from the iteration scheme, that is the value of p at this node, okay. And then you move on to the next node. You have a, if for example, if I made this node red, I have another search window which could potentially overlap with the previous search window where I am doing the same type of search, and I get another value for p bar here, okay. So, that is the idea, very simple in principle, and once you are done you have a grid of values for the vector p. So, that gives you the full field displacement and deformation displacement gradients. So, that is basically a the iteration scheme that underlies most DIC implementations. Now, of course, there are nuances in the actual implementation. There are things you have to take care of. For instance, you have to do a little bit of pre-processing, things like filtering, masking and so on, and you have to do a little bit of post-processing for interpolation and things like that. So, what we will do in the next session is I will walk you through a sequence of steps with a couple of sample images. I will show you what each step does, how the iteration scheme progresses, and what you will get at the end, okay, so that you can perhaps use this as a starting point for your own implementation. And once that is done, we will also have a demonstration session showing you how to use an open source code for doing many of these calculations if you are not up to writing your own code.